Okay, let me show you the contents of this video which I am going to cover. First, I will explain what is image watermarking. Then I will explain the types of watermarking and challenges in image watermarking. Then I will explain the discrete wavelet transform based spectrum watermarking for grayscale images. Then I will explain the watermark embedding and extraction algorithms. Then I will show you some performance evaluation parameters for watermarking process. Then I will discuss one Matlab code to implement the watermarking, complete watermarking process that will include embedding and extraction of watermark. And in the last, I will show you some results of execution of this Matlab code. So let's go ahead. So first, let's see what is the image watermarking. The digital image watermarking can be defined as a process of embedding a watermark into the main image. So this watermark can be a text string, it can be an image such as logo, or it can be an audio stream also. So the embedded watermark can be either visible or invisible depending on the requirement, and this watermark can be detected and it can also be extracted from the host image. So here we can see the watermarking process. So this is our watermark, a simple a small binary image having some content such as some text. This can be embedded to your main image, which is also known as a cover or image or host image. So this watermark is embedded, and if needed, this can also be extracted. So here you can see that watermark is not visible. So obviously this is the case of the invisible watermarking. And now let us see what are the different objectives of doing the digital image watermarking. The first is quite obvious, that is the copyright protection. I mean, identifying the real owner of an image. And the source tracking. This is quite interesting because we embed different watermarks to different sources. So we can identify a leaked media because we can identify or recognize the corresponding watermark, and we can have idea that from which source this media is leaked. And third one is the broadcast monitoring. Television news often contains watermark video from the international agencies. So this is the overall watermarking process. Here you can see that you have a cover image in which you want to embed the watermark. This is a watermark image. So with help of some secret key, the watermark embedding algorithm embed this watermark into the image. So you get the watermark image, let's say IW, and this is transmitted over the channel. And here at the receiving end, the extracting watermark algorithm is running, which requires the same secret key which was used during the embedding. And this watermark extraction algorithm can extract your watermark with or without cover image. So if cover image is required, it is known as a non-blind watermarking. If nothing is required except the secret key, then it is known as the blind watermarking. And the hackers will try to attack your watermark image with the objective to destroy the embedded watermark. Okay, so a robust process is one which can withstand against various attacks given on the watermarked image. And now let's see what are the different types of watermarking. So this is a chart. So according to the working domain, you can classify as a spatial domain and the frequency domain watermarking. And depending on the host type, you can say that it is a text watermarking, image watermarking, audio watermarking, or video watermarking. And according to the human perception, you can say it is visible or invisible watermarking. And invisible has the two categories, either fragile or the robust watermarking. According to the application, it can be a source based or destination based. And watermarking technique, on the basis of that, you can say it is either blind, semi-blind, or non-blind. So in this video, I'm going to cover the frequency domain approach. For that, we will use the discrete wavelet transform to represent the image in frequency domain. And we'll go for invisible watermarking. source based, and we will go for the blind watermarking, which is robust, and of course for image watermarking. And now let's see different challenges of an efficient watermarking. So the objective of a good watermarking process is to embed a watermark with the minimum possible changes in the quality of host media. I mean, watermarking process should be such that it should not change or alter the host media too much. So it should have the maximum capability to withstand against a variety of attacks on the host media, as I said. I mean, it should be the robust enough. Now, an efficient watermarking method simultaneously fulfills following three requirements. One is the payload, imperceptibility, and the robustness. Payload means that how much amount of information we can embed into the host image as watermark. And imperceptibility means that after embedding watermark, how much changes are given to the host media. And robustness, as I said, that its capability to withstand against a variety of attacks. So here in this graph, you can see that you have the three requirements. One is the imperceptibility, payload, and robustness. So a good or efficient watermarking process must be able to satisfy all these three requirements, and should maximize also. So this is the problem of placing an optimal point in this 3D space. So that means it should have the maximum payload, it should have the maximum robustness, and it should have maximum imperceptibility. But the problem is that if you increase the payload, your imperceptibility go down, and if you increase the robustness, again your imperceptibility go down. So that's the problem. So if you increase one quantity, other is affected. So these are the challenges of an efficient watermarking. And now let's see how we have used the discrete wavelet transform for watermarking. The discrete wavelet transform, as we know, that it is used to represent an image in frequency domain. So an image is decomposed into the four coefficient matrices if it is decomposed by a discrete wavelet transform. So we get four matrices. The one is the approximation coefficient matrix, that is known as the CA, then horizontal detail coefficient matrix, that is known as the CH, vertical detail coefficients matrix CV, and the diagonal detail coefficient matrix CT at any decomposition level, let's say N. So for watermark embedding, as I proposed in this video, we will utilize this diagonal detail coefficient matrix CDS for watermark embedding because it provides the best imperceptibility. Also, it is observed that a single level wavelet decomposition is sufficient for better robustness against attacks. So we will go for n equal to 1, and we will utilize the diagonal detail coefficients for watermark embedding. And the wavelet used for watermarking will be the Bayer 6.8. Actually, it provides the linear phase for better reconstruction. You can use other wavelets also. You can do a comparative analysis also that which wavelet is giving the better results in this watermarking process. And now let's see what is the spread spectrum watermarking. Actually, the concept of the spread spectrum watermarking was given by the I.J. Cox in his paper Secure Spread Spectrum Watermarking for Multimedia, which was published in IEEE Transactions in December 1997. And this proposed watermarking process in this video is actually inspired by this work of I.J. Cox. So the corresponding research paper can be downloaded from internet. It is available. I have given its download link in the description. You can go for that. Actually, this paper says that a watermark should be constructed as an independent and identically distributed Gaussian random vector or noise that is imperceptibly inserted in a spread spectrum like fashion into spectral components of image. Actually, instead of adding the bits some watermark image into the spectral components of the image. Here he suggests that we should add some Gaussian noise into the spectral components of image, which is just similar to the process of inserting Gaussian noise into the spectrum communication. So that's why it is known as the spread spectrum watermarking. So it is done to achieve more robustness. So for more detail, you can go through his paper. So that describes each and everything. And now let's see the type of watermark and the limitation of this spread spectrum process. Actually, the watermark that can be used for this type of watermarking should be a binary image of small size. For each binary bit, I mean the 0 of watermark, a Gaussian noise vector will be added to the spectral coefficients of an image, as I said. Therefore, to achieve imperceptibility, we cannot add too much Gaussian noise to the host image. Otherwise, it will spoil its imperceptibility. So, this is the main limitation of the proposed watermarking scheme, that only a small binary image can be used as watermark. For proposed scheme, we have used the following watermark image of size 20 by 13 pixels, and this is one. So this is a small binary image which is carrying this text ET. You can take any image, any binary image containing anything, but it should be small enough. Okay. And now let's see the watermark embedding algorithm, that how we can add the watermark. So it's quite simple. So you have first your host image, that is your grayscale image. Okay, so it is unsigned integer 8 grayscale image. First it is converted into the double format, and then we decompose this image using single level DWT, discrete wavelet transform. So we get 4 matrices: approximation, horizontal detail, and vertical detail coefficients, and diagonal detail coefficients. So as I said, we will use this CD matrix for watermark embedding. And also we need this binary watermark image. It is a 2D image, of course, and first it is converted into 1D row vector. Okay, so let's say if its size is m by n, so it will be of size 1 by m by n, and a seed is initialized, which will be used as a key. And this seed will be used to reset the PRN, I mean the pseudo random number generator of the software. And after that we will generate the pseudo random sequences. So now what we will check, so we will take each bit from this row vector of watermark image. So let's say we take first bit of this watermark and we check it for whether it is 1 or 0. So if it is 0, then we do this operation, we add the watermark. I mean we add the pseudo random sequence PRN multiplied with this k, which is some constant, and which will be known as the watermark embedding strength. And now this multiplication k into PRN will be added to your diagonal detail coefficients like this. And let's say if the second bit is 1, then we do not add the PRN to the CD. And if we go for the third bit, if it is 0, then we will generate a new PRN, and again we will add this to the CD. So this is how we can add the pseudo random sequence for all binary bit which are 0 in this watermark vector. So this process is simple. So after adding all the PRN sequences to CD1, we take this CD1 dash and these 3 matrices are already there which are unchanged. So along with this CD dash, we take one label in inverse discrete wavelet transform to get our watermark image IW. So this is our process of watermark embedding, which is easy. Now let's see the watermark extraction algorithm. So this is watermark extraction algorithm. First we need the watermark image IW, and since it's a blind process, so we don't need any other thing. I mean, we don't require the host image for the watermark extraction. We just need this secret key. So that is the seed. So same seed will be used here, which was used for watermark embedding. So with help of that seed, the PRN generator is initialized and we generate the pseudo-random sequences. And now we will initialize a row vector which is equivalent to the size of your original watermark, that is 1 by m by n, and we initialize this vector to the 1. I mean, the all bits are equal to 1. So this is fully white in color. Okay. And now what we do, so we first decompose this watermark image into the wavelet coefficients. So using one label DWT, we get 4 matrices. I mean CA1, CH1, CV1 and CD1 dash, because it is already modified in the previous process. We do not require these 3 matrices, so no need to extract them. Only we need the diagonal detail coefficients. So what we will do now, so we find the correlation between this CD1 dash and the PRN which is generated here. So we find the PRN and we get the correlation value and we store into the vector R. So we generate for all watermark bits. So we generate PRN for all watermark bits. So if there are, let's say, 1000 bits here, we generate 1000 PRN sequences and we get correlation with the CD1 dash. So all correlation values are stored in this vector Ri, and then once it is completed, we get a mean of this. So we find this T, which is known as a threshold value. So now to retrieve the watermark, we do this operation. We compare each value of R with this threshold. If R is greater than threshold, then we flip the watermark bit from 1 to 0. So if this watermark bit first one is 1 and we satisfy this condition, then it is flipped to 0. So we do for all watermark bits depending on this condition, whether it is satisfied or not. And once this process is complete, your watermark is retrieved. So that is Wm dash. And since it is in a 1D row, so to get the image, we reshape it to make it 2D. And now this is your recovered watermark WMR. So this is a simple process of watermark extraction. Now let's go for the performance parameters. To judge the performance of a watermarking process, following 2 parameters are widely used. So one is the PSNR, that is the peak signal to noise ratio, which is calculated between the host image and the watermark image. And the high value of PSNR obviously represents the high imperceptibility, and that is required also. And second is the normalized correlation coefficient and CC, and the simple correlation coefficient CC. So it is computed between the original watermark and the recovered watermark. So it indicates the robustness of the process. So as we know that correlation coefficients is found in the range 0 to 1. So its more value near to 1 represents more robustness of the process. So now let's see how we can compute these 2 parameters. So PSNR for 2 grayscale images, let's say your original image and watermark image of let's say size m by n can be computed by this formula. So PSNR equal to 10 log 10, 255 square upon MSE. So 255 because the maximum value of any grayscale, 8-bit grayscale will be the 255. Where MSE is the mean square error, that is given by 1 upon mn sigma I equal to 1 to m, j equal to 1 to n, and then having the difference of pixel to pixel values and then squaring it and adding all the values and having this average. So that is the mean square average. And as you know that PSNR is by this formula, it is seen that it is expressed in the dB decibels. So now let's see the correlation coefficient formulas. The simple correlation coefficient between original watermark WMO and the recovered watermark WMR can be computed by this formula. It's a standard correlation coefficient formula, and the normalized correlation coefficient NCC is given by this formula. Actually, in the literature, many researchers have used this formula for their research paper. The relationship is simple that NCC is another form of CC, where just these average values are omitted from the formula. So this is known as the normalized correlation coefficients. So it is quite easy to compute. And now let's see the different types of attacks to destroy the watermark. So to evaluate robustness of watermarking process, some image processing attacks are performed on the watermark image to destroy the embedded watermark. So let's see what are those attacks. The first one is the filtering of watermark image. So you can make it blur by averaging filter, you can make it sharp, you can go for median filtering, etc. And the second is the compression, that is quite common. You can go for the JPEG compression. So you can save the watermark image with the different compression ratios to destroy its quality. And noise addition, another very common. So you can add some noise such as salt and pepper or Gaussian noise to the watermark image, and you can see whether you are able to extract your watermark or not. Then cropping is again quite common, and you can resize your image, and you can change the intensities. I mean, you can go for the histogram equalization of image, or you can do some intensity modification of the watermark image. So these are few common attacks which are considered by the majority of research papers in the watermarking. So I will also implement all these in my code. So I will explain in the code section. So now let's come to the programming part. So this program is implemented in the Matlab, and let me explain the code. So first we will read your cover image with the UI get file and ImRead. So that will go into the variable cover image. I have made one clone that will be used for display purpose, and then cover image is converted into the double format that will be required for DWT and calculating PSNR. And then we are reading the watermark image again with the UI get file and ImRead. So the watermark will go into this watermark, and I'm making a copy of it that will be required later. And this is the decomposition label, n equal to 1 just now. You can experiment with the more decomposition labels. And L equal to 2 power n. So this L will be used to reduce the size of the coefficient matrices depending on the decomposition level n. And this is the wavelet type Biot 6.8, bi-orthogonal 6.8. You can use any other wavelet, and you can have one comparison also. And this is the k equal to 2, which is the embedding strength. So again, you can try for different embedding strength, and you can study that what's the effect of this k on the watermarking process, particularly on imperceptibility. So here I'm getting the size of the cover image, and here I'm getting the size of watermark. And this 2D watermark is here now converted into 1D row vector. Okay, so WM vector is actually your watermark in a one row or one column. And now this is the watermark embedding process. So first your key is initialized. It has some number. You can go for any other number. So with this key, this random number generator RNG of Matlab is initialized, and then we generate the PN sequences, I mean pseudo random noise sequences by this formula, which is 2 into RAND. RAND function of Matlab is used to generate the random function or random numbers. And we do this mathematical operation. So this matrix is multiplied by 2, and then 0.5 is subtracted. Why this is done? Because the Cox paper I mean that I.J. Cox paper. He says that for better recovery, your pseudo-random sequence must have only these three numbers, either +1, -1 or 0. So this mathematical operation is done to convert your random vector for having only these three values, because Matlab's random function will generate any random number in the range 0 to 1. So it can generate, let's say, 0.1, 0.560 and something else, anything between 0 and 1. But requirement is that we need only the +1, -1 and 0. So to achieve that, this operation is done. And here the DWT mode is defined, that is a periodic. And now wavelet decomposition is done using the WaveDAC2 for this cover image for the label N with the wavelet specified. So we are extracting the approximation coefficient, and here we are extracting the horizontal, vertical and diagonal detail coefficient. So obviously we will use this CD1 matrix for watermark embedding. And now this is the actual watermarking process. So here we are adding the PRN sequences to CD1 for each watermark bit which is equal to the 0. So here we are checking whether watermark bit is 0 or not. If it is 0, then we add this PN sequence multiplied with the embedding strength K to your CD1 matrix. So this process is repeated for all 0 bits, and for each addition the new sequence is generated. Okay, and with these lines of code we are just getting our image back. We are inserting this modified vector CD1 dash after adding so many PN sequences to it, and then collecting all these CA, CH, CV and this modified CD1, and then inserting back into these variables C, which we obtained from the wavelet decomposition. And with help of it, again WaveRAC, that is the inverse discrete wavelet transform. So with help of this WaveRAC2, with this C1 and S1 that were actually obtained using the decomposition, and of course the C1 is modified because of this CD1 dash, and with the proposed wavelet we get our image back. So that is a watermark image, but it is in a double format. So it is converted into unsigned integer 8 format for display purpose. So this is my final result, watermark image unsigned integer 8. So that is watermark image. Okay, now this is the attack section where we have applied various attacks on the watermark image. So here you can see that you can add some noise with help of IMNoise function, such as salt and pepper noise with the required strength. Actually here you can see that these all are of green colors. It means all are made comment, because I'm not executing them to display the watermark process. If you want to apply some attack, you just simply uncomment one line at a time. Okay, so or you can apply the multiple attacks to the image also. For example, if you want to add salt and pepper noise and Gaussian noise simultaneously, you just uncomment both the lines, so it will be a double attack on your image. Okay, so this is for cropping, and this line will be used for applying some filter on the image, I mean the filtering process. So for that you need the mask. So I have used the two masks. You can uncomment and any one at a time. So if you uncomment this average, it means your image will go blur, and if you uncomment this mask, you will get a sharp image after this sharpening process. And this image, this line is for median filtering. So this will be another attack, and this is for histogram equalization. And this line is actually writing your watermarked image into the current directory with the name dwt watermark.jpg. Here I am using the quality factor 100, so it means I am not providing any JPEG compression. So if you want to provide the JPEG compression, you can change this quality factor. So if I use quality factor 80, it means your quality of JPEG images gone down. So you can go for 80, you can go for 60, 50, 40, and at let's say you can go further, and then you can check the quality of your retrieve watermark in this case of image compression. And with these lines of code, I'm calculating the PSNR between the watermark image and the original image. So first we are finding the MSE, mean square error. So here you can see that watermark image and the covered image, and then we are finding the maximum intensity level out of these two, and then applying this formula as I have already shown you in the previous slide. So that is a 10 log 10, the maximum intensity square upon MSE, and printing this PSNR value in the workspace. And here I am displaying the images, I mean the original and the watermark images. And now the watermark recovery process. So this code is for watermark recovery. So first we are reading our watermark image by this IamRead function. So watermark image goes to this variable watermark image. Now we are getting its size, and then we have already these two variables, I mean the size of the watermark, and with help of this we are initializing a watermark row vector, as I said, and each value of this having the logical 1. It's a complete white in the color. So this is your initialized watermark vector. Now we are decomposing this watermark image into the wavelet coefficient matrices using WaveDAG2, and out of these we are extracting only the CD2. I mean the diagonal detail coefficients. As I said, watermark was embedded only in this DWD coefficient. So we need only CD2. Now we are initializing this key. It is the same key which was used in the watermarking, watermark embedding process. And then with RNG, we are initializing the state of a random number generator. And then we are generating the PN sequence with help of this RAND Matlab function. And here we are finding the correlation between all the values of watermark bit. So for all the values of watermark bit, we are generating PN sequence, and we are finding the correlation between CD and PN sequence and storing all the values in this vector correlation. In the theory slide, I use R variable for this, if you remember, and we are generating PN sequence, new PN sequence for all comparison. And once this process is complete, all the correlation values are stored in this correlation vector. With help of that, we are taking mean of those values to find this threshold value. And with this 1.5 multiplied with the T, it means that your threshold value is slightly elevated. I have found that by elevating this threshold, we get the better recovery of watermark, and then defining a threshold vector for display purpose. And then we are displaying the all correlation value, I mean correlation vector, and this a straight line which is representing your threshold. And here we are retrieving our watermark. So for the full length of the watermark, I mean for all watermark bits, we are comparing this correlation values which are stored in correlation vector with the threshold. So if correlation is greater than threshold, we flip the watermark bit. As I said, it is initialized to 1. If this condition is satisfied, then it is converted into 0, I mean the black, white, from white to black. So this operation is completed for all watermark bits. At the end of this, you retrieve your watermark. So since it is in a row vector, it is reshaped to 2D. Okay. So this is our watermark WMR. So here it is plotted, original watermark as well as a retrieved or recovered watermark. Now with these lines of code, we are finding the correlation between the original and recovered watermark. So with help of Matlab inbuilt function car2, we are computing the simple correlation coefficient. So that will go into the CC, and then with help of appprintf we are printing its value, and with these lines of code we are finding the NCC, that is a normalized correlation coefficient, where all the mean values are dropped, and with help of printf we are printing this value NCC. So this is the complete program of the watermark embedding, giving attacks, and the watermark retrieval. So now let's see some result. So this is one result. This is your original image of paper, and this is a watermark image. So you can see the quality is almost same. Visually there is no difference. So you can say that the proposed algorithm is quite imperceptible. And if you compute the PSNR between these two, you get this value 30.93 dB. Okay. This is for embedding strength k equal to 2. So if you decrease this k, embedding strength, your PSNR will go up. But at the same time your robustness will also go down. So you have to do a proper choice for that. And this is your original watermark, and this is the recovered watermark. You can see both are same. Here I have not given any attack. Okay, so the correlation of course will be the 1 because both images are same, and normalized correlation is also 1. And in this figure you can see all the correlation values which are compared with this threshold. So this red line is showing your threshold, and here you can see all correlation values are I. So if your correlation value is greater than your threshold, the corresponding watermark bit is flipped to 0. So at all these instances where the value is greater than threshold, you get 0 watermark bit. Otherwise the watermark bit is white. So this is how you recover your watermark. And here you can see its robustness. So for that I have taken this image of Lena, and this is my watermark. So I have applied the salt and pepper noise to this cover image with a strength 0.02, and this is my recovered watermark. So it is fully recovered. That's why CC is 1 and CC is 1, and I have added the Gaussian noise also with the variance 0.01. I have again recovered the full watermark, so CC1 and CC1. Sharpening also has no effect. I am getting full watermark. Now, but averaging, blurring this image destroy this watermark. So the CC of course will reduce, that is 0.76, and NCC is 0.91. But still we are able to recover the majority of the watermark. Okay, it's quite obvious because we have embedded our watermark into the diagonal detail coefficients, and as we know, the diagonal detail coefficient represent the high frequency component of an image. So by doing the blur operation, obviously your high frequency components will be removed. That's why our this watermark is destroyed, but it is not too much degradation. It is quite acceptable. And this is the cropping. You can see that the 1/4 of the image is completely removed. Still we are getting our watermark fully. And then applying the median filter, again it is attacking on the high frequency components of the image. So we are getting some distortion in the watermark. So CC is 0.94 and NCC is 0.98. And with JPEG compression, so we have use the quality factor 50. So we are getting very less distortion in the recovered watermark. Even we can go further down, we can go for 40, 30 and even 20. So I request you to just try with a different Q factor for JPEG compression and see how much degradation you achieve in recovered watermark. So this is a result, and now let me take you to the Matlab, and where I will show you that how we can run this program and what type of output we can achieve. So this is my program and it is already written, so I will simply run it. So it is asking me to choose the cover image, so I am choosing this pepper, and watermark is selected. This is my watermark ET, you can see, and I will get the result. So okay, so this is my original watermark and this is a recovered watermark. So it is recovered fully. Obviously correlation will be the 1, and here you can see the correlation pattern, and this red one is the threshold value, representing threshold value. And here you can see the original image as well as the watermark image. So quality wise there is no difference at all. Both the images are almost same, but they are different. So we'll get some PSNR value. So let me go to the workspace and command window, and here you can see the value. So this is the PSNR, which is 30.939731 dB, and here we are getting the correlation 1, obviously because we have achieved the full watermark. So now let me run it again, and let me choose another image. Let's say this baboon is my cover image and this ET is my watermark. And again I'm getting the full watermark, so correlation will be 1. This is correlation pattern, and here you can see that this is original image and this is watermark image. Okay, so we can see the PSNR etc. here. So PSNR is 30.45 and the correlation of course will be 1 for the watermark retrieval. Now let me show you giving some attacks. So first I will add some noise. Let me add the salt and pepper noise. So I will uncomment the first line. So it will add the salt and pepper noise with the strength 0.02. So let me run this program and choose the Lena image as the cover image, and ET is my watermark, and this is the result. So again I'm getting my full watermark. It means there is no effect of adding this salt and pepper noise. So here you can see. So you can see that this is your original image and this is the watermark image, which is corrupted by this salt and pepper noise. You can see lots of whites and black dots as a salt and pepper noise here. So let me try one more attack. I will add now Gaussian noise to it. So I can run this again. So let me take Lena again and ET watermark, and again I'm getting the full watermark of course, and this is the original and the watermark image. So here you can see that Gaussian noise is added, which has corrupted this noise. So I can show you a zoom version of it. So this is the original image you can see, and this is your an image which is corrupted by the white Gaussian noise. So even in this in the presence of this white Gaussian noise, we are able to recover our watermark fully. So that is showing the robustness of this proposed watermarking. Now I will show you the cropping. So I can crop the 1/4 part of your watermark image. So let me choose another image, Barbara, and ET is my watermark, and again I achieved my full watermark, and you can see that this 1/4 of the image is completely removed. Still I'm carrying my full watermark. So that is the robustness of this proposed scheme. You can go for further cropping. And now let me try one more attack. So let me show you the averaging. So I'm uncommenting this mask and this IM filter line. So now I'm applying the averaging. I mean the 3/3 averaging. That will make our image blur. So I'm choosing this Lena again and ET watermark, and let's see what I will achieve. Okay, so this destroyed my watermark, but not too much destruction. This is a correlation pattern. You can see the variations, lots of variations, and here you can see that this is the original mark and this is the watermark image. So obviously it is quite blurred as compared to this original watermark, and you can check for correlation. The correlation of course is dropped from 1 to 0.764, that is a CC, and NCC 0.9173. Okay, now let me try one more attack. So I can try the JPEG compression. So here in this line you can see that I am writing the image with the quality 100. So if I can drop this to 50, it will drop the quality of image, and let me check the watermarking robustness. So I am taking this paper image ET watermark, and let's see. Okay, so with the 50% quality I achieved this watermark. It is quite acceptable. Very few bits are distorted, and this is the original image and this is watermarked image. Okay, and now let me further drop it, let's say 20. So only the quality factor is a 20 for this JPEG compression, and let me choose again this paper and watermark ET. Okay, so at this point it is quite distorted, and let me check the values. Okay, so the correlation becomes 0.4. It is quite less, but it's still it is giving me idea that something closely with ET was written or embedded in the image, and normalized correlation coefficient is 0.77. So this is how you can watermark your image, or you can apply various attacks to the image. You can apply the multiple attacks also. So let me show you the salt and pepper noise is added as well as it is cropped. So I am applying the two attacks simultaneously. So let me run again and choosing the Lena and ET watermark, and surprisingly I am getting my watermark fully, and this is, you can see that the 1/4 is removed and the noise is added. So the two attacks are there, and still I am getting my watermark fully. So we can say that this proposed algorithm is quite robust, which can survive against various attacks. So this is what I have covered in this video. I hope you have enjoyed it and learned this watermarking process. So this is just framework I have proposed. You can modify it, and you can even go for its more refined version. I will welcome. So that's it for this video. I hope you have enjoyed it well. So thank you watching this video. I request you to please like it, share it. Thank you very much. Have a good day.